All right, welcome back. In our last discussion, we got the big picture view of the Kalman filter. Today, we're rolling up our sleeves and diving deep into the core mathematics that make this thing tick.
So let's get right to the heart of the problem. You've got two pieces of information, right? You have a prediction, what your model thinks is happening, and you have a measurement from a real-world sensor. But here's the catch. Neither one is perfect. They're both a little bit noisy. So who do you trust more?
Here's how we're going to break it down. We'll start with the problem we're trying to solve, then look at the key equation, demystify this thing called the trust dial, and finally we'll see it all come together with a simple traffic example.
Okay, so first up, the blending problem. This is really what the Kalman filter was born to do, to find the single best version of the truth when it's being told two slightly different stories.
You're basically stuck in the middle. On one hand, you've got your system model's prediction, which has its own flaws, what we call process noise. And on the other hand, you have a sensor reading, which has its own measurement noise. The actual true state is hiding somewhere between them.
So mathematically, this is what our prediction looks like. It says the new state is based on the old state, plus any known control inputs. But see that little W at the end? That's the important part. That represents all the random, unpredictable things, the process noise. And we quantify the uncertainty of that noise with the letter Q.
And on the flip side, we have our measurement. This equation connects the true state to what our sensor is telling us. And that V term? That's the sensor's imperfection, the measurement noise. The uncertainty of this part is what we call R.
So, we have a prediction with uncertainty Q and a measurement with uncertainty R. How do we mash them together? Well, the answer starts with this beautifully simple blueprint, the update equation.
This is it. This is the heart of the filter. And it's actually pretty intuitive when you look at it. It says our new updated estimate is just our old prediction plus a correction. That's it. The whole secret is figuring out the size of that correction.
So let's walk through it. Everything starts with our prior estimate, xt minus star. This is just our model's best guess, our prediction, before we look at any new data from the sensor. Then comes the really interesting part. This term in the parentheses. This is the difference between what our sensor actually measured and what our model predicted it would measure. You can think of it as the surprise. It's a measure of how wrong our initial guess was.
And that surprise gets multiplied by our magic ingredient, KT, the Kalman gain. This single value is the key to everything. It decides exactly how much of that surprise we should pay attention to when we make our correction.
Which brings us to the Kalman gain itself. I really love this analogy of a trust dial, because that's exactly what it is. It's this incredibly smart mechanism that decides moment by moment how much to trust the prediction versus how much to trust the new measurement.
And that, of course, is the million-dollar question. How do we set this dial? We don't just pick a number. The whole power of the Kalman filter comes from its ability to choose this value optimally in a way that is mathematically guaranteed to give us the smallest possible error in our final estimate. And here's the famous formula for it. Now, I know, that looks like a monster, but don't get bogged down in the symbols. The intuition behind what this equation does is actually incredibly elegant. Because this is how that trust dial works in practice. It's a beautiful balancing act. Think about it. If your sensor is really noisy, meaning its uncertainty, R, is high, the Kalman gain automatically gets smaller. It dials down its trust in that unreliable sensor data. But on the flip side, if your prediction is the shaky part, if its uncertainty P is high, the gain gets larger. It dials up its trust in the new measurement to fix that bad prediction. It's just so smart.
Okay, enough theory. Let's make this feel real. We're going to use a super simple traffic example, trying to estimate the number of cars waiting at a red light.
So here's our situation. Our traffic model predicts there are 20 cars in the queue, but it's not super confident it has a variance of 9. At the exact same time, a sensor in the road measures 25 cars, and this sensor is more reliable. Its variance is only 4.
All right, let's crunch the numbers. 3 quick steps. First, we calculate the Kalman gain. We plug in our uncertainties of 9 and 4, and we get a gain of about 0.69. Next, we update our estimate. We start with our prediction of 20, and we add the surprise of 5 cars, but we only add about 69% of it. That gets us to 23.46. And finally, we update our own uncertainty for the next time around.
And there's our answer, a much smarter estimate of about 23.5 cars. Now notice what happened here. The answer isn't 20 and it's not 25. It's a weighted average that's pulled much closer to 25. Why? Because the sensor was the more trustworthy source of information.
And this right here is the real payoff. This is why we do all this.
We started with a prediction uncertainty of 9, but after fusing it with the measurement, our new combined uncertainty has plummeted to just 2.77. We have a much more confident estimate than we started with.
Look, this isn't just some clever trick. It's a statistically optimal way to combine information. What the Kalman filter does is proven to be the absolute best linear estimator you can have under these circumstances.
Just think about that number again, 2.77. That isn't just a better number, it's the best possible number. By using that optimal Kalman gain, we have squeezed every single drop of certainty out of our data. There is no other linear way to combine this information and get a more confident result. That's the power we're talking about.
So let's just quickly recap. The update equation gives us a simple framework to blend our prediction with our measurement. The Kalman gain acts as that perfect trust dial, weighting the blend based on how uncertain each source is. And the incredible result is that we always end up with a better, more certain estimate than we started with.
Now, this mathematical backbone is unbelievably powerful for systems that behave themselves, systems that are nice and linear. But that leads us to the next big question. What happens when the real world gets messy, chaotic, and nonlinear? What do we do then?